Okay, so lecture this morning, forgot to press record. So this is going to be just a talk over of the lecture notes we did this morning. Um, Up to this point, we've been doing integration techniques like substitution, integration by parts, some trigonometric integrals. We did skip true trig substitution, but we came up to partial fraction decomposition, which is partially a lot of algebra as well as um, some useful stuff when we're doing integrals of specific types. And so let me jump through the first part. These are all review. I can let you read that. We want to look at rational fractions or rational functions. So that's one polynomial divided by another. And the integrals of these things can be complicated, and partial fractions can help it sometimes. So this morning, when we went through this, we mentioned that partial fraction decomposition is kind of like a reverse common denominator. So we've been doing lots of reverse stuff, like the substitution is kind of like reverse chain rule. Integration by parts is reverse product rule. This is like reverse common denominator. So when we did do common denominator back in algebra, it's combining two fractions, 1 over x minus 2 and 1 over x plus 1. We did this trick of multiplying by 1 twice, and so that just means multiply the top and the bottom by the same thing. In the first one, it's x plus 1 on top and bottom. The second one, it's x minus 2 on top and bottom. So when you multiply the bottom out, you both times get the common denominator that you're trying to find. If you then multiply the top out, so you distribute the 1, in each case, you get x plus 1 and x minus 2. So when you combine those, it's 2x's and minus 1. And so that's the process of combining the denominator. If you wanted to go now the opposite direction, it's kind of like the denominator's already been combined, and you want to break it back out into the two component fractions. So here's a new example where you have 1 over x squared minus 1. You notice the bottom does factor as x minus 1 and x plus 1. So can you, and the answer is yes, but how do you break this back out into the two fractions with separate denominators? And really the catch is what is on top? Because what is the top of each of these things look like? What's the numerator look like? So we went through, we made some guesses. We guessed that, well, can we just break them up where they're also 1? And we ruled that out by multiplying, by top and bottom, by x plus 1, x plus 1, x minus 1, x minus 1 onto our parts. And when we recombined, we got 2x over the denominator, not back to 1. So that meant that that decomposition didn't work. But we did notice that the x's combined because when the tops were both multiplied out, we got an x and an x. So in order to get rid of them, we might guess that it should be like a 1 and a minus 1. And at least then they would cancel the x's out if we just reversed this. This one was a minus 1. It seems like it might work. So we guessed that, and then we checked. And it also didn't work, because when we multiply to get the common denominator, the x is canceled, but we had a 2 left over. Now, in a lot of the classes, when you have a constant multiple, that can be dealt with. You can do some divisions, you can move numbers around. X is not so much. So instead of all of that, instead of giving the actual answer, we guessed, look at that. And they should both be opposite signs, but if instead multiplying by 1, if we multiply by half. Still, it's guess and check, but it's developing intuition. When we do the actual common denominator here, x plus 1 over x plus 1, x minus 1 over x minus 1, and distribute out. The x's cancel. It's a half x and a minus half x. But then the numbers are half and another positive 1/2. So they do combine to be 1. So this is the correct, what's called partial fraction decomposition of your original into the two parts. So that worked. And then why do you do that? Well, if you tried to do this integral 1 over x squared minus 1, It's not in our table. Use substitutions don't work. Integration by parts doesn't work. It's definitely not a trig thing. So when we realize that we can do this partial fraction, then just replace the inside, the integrand, with the two parts that we just decomposed. And if we get to this point, then we can factor out these halves, break it into two integrals, and each one of those is very straightforward. Just natural log and another natural log, and boom, we got it. So in order to get this original problem, we had to break it into two pieces, and it's weird that we got log, but that's just the way it kind of happens sometimes. Integration is just, it's unexpected, it's weird. So now, in general, we can work on the intuition, and that's fine. Or we realize that if we were going to break up a problem like this, so we're trying a new one here, 1 over x squared plus x, we know that when we factor, we get x and x plus 1. So that's at least a hint that I need to do the same sort of process. Some fraction with x, some fraction with x plus 1. But instead of guessing and checking, let's just put in some placeholders. So call it a and b. And if this really is fine, the reverse common denominator, then we just work the common denominator forward by multiplying by x plus 1 over x plus 1 and x over x. And we get to this part. We get to this final fraction, which has a's and b's in it. But at least the denominators are the same. So when I say find the common denominator and solve, it means get two fractions and then realize that if the denominators are the same, then the numerators have to be the same as well. So we set the numerator, so I just recopied it here, reset the numerators to be equal. So if I set these equal, I'll get that 1 is equal to ax plus a plus bx. So that's this line right here. Now, do a little bit of regrouping here. Maybe you can skip down to here. We have two x terms, which we combine into a plus b quantity x. And we have this term over here that doesn't have x. We call that the numerical term, which is a. Now, in this line, you can see they're equal to 1. But whenever you have a polynomial on both sides, you compare the x terms and you compare the number terms. And I do have the number terms, a and 1. But the x term on the right is a plus b, and there is no x term on the left. So technically, we could write in 0x. So that means that whatever we have for a and b, they better cancel out because there's no x's left. So we just realize that that means that the a plus b has to be 0. And a and b have to be the same but opposite sides. And when we look at the number terms, well, a is just straight up 1. So we get this system, very small system of two equations and two unknowns. A is 1, substitute in and solve for b, we get b equals minus 1. And so if we combine those, we had our placeholders before, we just put in the actual values, and we can confirm that this is the partial fraction decomposition of this original fraction into two smaller fractions. And once again, if we wanted to integrate the left side, we could just integrate the right side and get these two natural logs out of it. Pretty straightforward. Okay, so let's just go a little bit more complicated. 1 over x squared minus 2x minus 3. Again, the realization that it factors, and then we can write this out into these two components, something over x minus 3 and something over x plus 1. Reverse common denominator. So how do you solve it? You do the common denominator by multiplying the top and bottom by the correct things to get to the denominator. And then multiply out the top and we get this slightly more complicated ax plus a plus bx minus 3b. But once again, since the denominators are the same and the fractions are equal, that means the top has to be equal. And therefore, we do the same thing. Group the x's, group the numbers, set the number terms equal to each other, set the x terms equal to each other, which once again is 0 on the left. So that means that whatever a and b are, they have to be a plus b equals 0. And a minus 3b is going to have to be 1. So you get a small system of equations, solve it out in your normal way with matrices or back substitution or whatever. You get that b is minus a quarter and a is a quarter, and therefore you end up getting this decomposition. You could either write as a quarter, or you can factor a quarter out, or whatever, but at least you have this. Where it gets more complicated, and I wish I could just, it just looks cluttered, but here's the original problem, 1 over x cubed plus x. And you do realize it factors, x and x squared plus 1. So here's the new catch for partial fraction decomposition. I'm not going to go through the intuition on why this is true, but the point is you can break this out into the two denominators, x and x squared plus 1, but the top ends up being a placeholder for a number. But anytime you have x squared plus 1 that cannot be factored further, in the lecture I just showed that you couldn't factor it at all. So irreducible is what it's called, or not factorable, or whatever term you want to use. But if this is a square that can't be reduced, the top will not just be a single number. It'll actually be a polynomial which is 1 less degree, so a monomial, meaning we need bx plus c. So once you realize that this is the form that you need, then we just went through the exact same process. Take your guess, multiply top and bottom by what you need, x squared plus 1, x squared plus 1, and x over x, and recombine it down into this form here. Once again, we set the denominators equal, they are equal, we set the numerators equal, and we end up getting this equation here, where 1 is ax squared plus a plus bx squared plus cx. And then realize that the x squared terms on the right, which is a plus b, has to be the x squared terms on the left. And there aren't any, so a and b have to add together to get 0. Similarly, the x term on the right, which is c as the coefficient, has to be 0, which is the coefficient on the left. So c has to be 0, and similarly, the number terms gives that a is 1. Very simple system. A is 1, so b has to be minus 1. C is 0. Plug it straight back into here, and boom, you end up getting this 1 over x and negative x plus 0 over x squared plus 1, and that combines to this b. And you'll have two integrals if this was an original integral, and those are much easier to do. So that's basically the end. The rest we went through some homework questions. I think that's probably a good place to stop. It does get more complicated if this factors in the denominator, if there's many more factors, or it's harder to factor. But otherwise, I think that sort of concludes the end of partial fraction decomposition.